I've got a question for you. Where are all the farms? Seems pretty simple, right? Like, we should definitely know the answer to that. But it turns out, in many parts of the world, we don't, which is a problem when you want to manage water or predict food supply or respond to a crisis. Because before you do any of that, you need to know one basic thing.
Where are the fields?
And answering that question is harder than it sounds.
There's just a huge variability in terms of data collection. And in many countries, there's just not data collected about this at all.
That's Hannah Kerner. She's a computer scientist at the School of Computing and Augmented Intelligence at Arizona State University. She uses satellite data and machine learning to create practical tools that do everything from map global agriculture to respond to disasters. I'm Pete Zrioka. This is Lab Coat Optional, the show where advanced research meets everyday curiosity. Today, how machine learning is being used to map the planet, understand our food systems, and make use of the crazy amount of data we already have to improve people's lives. Hannah, welcome to the show.
Thank you.
So you sit at the intersection of machine learning, remote sensing, and sustainability. I would like to start by breaking down some of those terms. When we talk about machine learning, it's not exactly equivalent to artificial intelligence, right?
Right. I think most people would agree that machine learning is kind of a subset of AI. Okay. However, today, machine learning has grown to be so much of the field of AI. Basically, we see like almost everything that is a subfield of AI involving machine learning in some way now that these terms have become kind of synonymous. But when we talk about machine learning specifically, we're talking about training some models to make predictions, to perform some task that is learned from data. And
I believe your PhD I think your PhD was in novelty studies, novelty
detection.
Novelty detection. So that would mean an artificial intelligence recognizing things that it wasn't different than what it was trained on?
Yeah. So basically, typically in machine learning, we're trying to predict things that we know we want to find already.
All right.
But in many cases, we don't know what the things we want to find might look like.
Yeah.
So, for example, if we're exploring other planets with the Mars rovers, which is one of the applications that I worked on and really motivated my work on novelty detection, we don't know what interesting scientific phenomenon are necessarily going to look like there. So in exploration settings, we really want to not just find, what it is that we know we're looking for, specific kinds of signatures, but we want to find what's new, what's not what we've seen before.
It's like kind of like avoiding confirmation bias, right? In the sense that like, we want to find this thing, so we're going to train the model to do this thing. And by training on novelty recognition, it opens up pathways for different discovery.
Yeah. And that's actually one of the challenges in evaluating how well novelty detection systems are doing is you're trying to avoid confirmation bias of like, well, when we look at the things that were novel, how do you assess, like, was this something that I would have been excited to find? So it's a really interesting area, not just in terms of developing the methods, but how you assess research improvements.
That's so cool. Okay, so and the other part of what you're working on is remote sensing. You're using remote sensing data. So when I think of remote sensing, I think of satellites. And when I think of satellites, I primarily think of imagery. But in practice, remote sensing encompasses much more than just satellites taking pictures, right?
Yeah. And usually for our work, we are talking about satellites because we're really interested in creating machine learning systems for processing data that comes from like the specific types of data sets and the opportunities that those present that are coming from satellites. So I think a lot of people don't realize that there are like thousands and thousands of satellites in orbit right now. And they're not just taking images like occasionally or of targeted observations. There are many satellites that are taking observations systematically. So they're taking pictures at the same time, at the same place, every day or every week or something like this. So we have these incredible data archives of, for example, from the Landsat satellite from NASA, images of every place on Earth every 16 days since like 1972. So they're continuously monitoring, continually acquiring this data. And then we have the archives just sitting there.
Is it the same satellite since 1972?
No, it's not the same satellites. Whoa.
Because like
they're up there.
Cameras have gotten better.
Yeah, well, cameras definitely have gotten better, but so yeah, that's actually an interesting thing with newer satellites that are trying to keep up with the pace of innovation here on Earth, being able to launch these satellites more quickly, and that's where there are a lot of companies like Planet Labs, for example, that launches satellites at a much faster cadence. So you can benefit from those upgrades at a faster rate. But like the Landsat satellite, we're on, I think, Landsat 9. I'm now forgetting, is it Landsat 9 or 10? But
illustrative of your
in any
point.
case, there have been several. And yeah, those are upgraded, and each time they're also upgraded to, incorporate new feedback from science teams that are trying to detect certain phenomena on the Earth.
Okay, that makes me very curious because you talked about Landsat 9 or maybe 10. We don't know. Yeah. I was going to ask if there's specific satellites that you use. Like, I mean, you don't have your own satellites. You're not launching your own. But also, like, I realize I don't know how researchers actually use the data that's being collected or get the data that's being collected by all the stuff that's whizzing over our heads all the time. Yeah,
I think what's incredible is how easy it is to access this information in terms of like it's publicly available and free. I think most people don't realize like a lot of these assets are public resources, provided by our government or the European Space Agency, other governments, JAXA, the Japanese Space Agency. All these different governments are providing these monitoring capabilities for free. Free. I mean, of course, as taxpayers, we're supporting that.
But it's a public service.
Yes, it's an incredible public good, and it drives so much research as well as industry, commercial products. There's so much value to that. There's actually been studies of like Landsat data used to be, it used to cost money, used to be privately held. And there's some studies on like what was the economic value of opening those data archives for those who are interested in that kind of assessment. But anyway, there are lots of different platforms where you can access these data. A lot of them are now stored in cloud platforms like AWS or Azure. Microsoft has Planetary Computer Data Catalog, private data sets, you access through APIs.
I mean, and also it's just fun. Well, if you're a weird nerd like me, it's fun because I've spent hours going back in time on like the Maricopa County Assessor's website and it's being like, oh, my house shows up here. And this part of my neighborhood was like an orange grove. And this is before the 51 cut through it and all this. So like, yes. I think it's fascinating stuff.
Totally. And I mean, a really easy way to look at that kind of thing is through platforms like Google Earth online or desktop, where you can just look at the historical imagery and see, so far back. I agree. That's super fun to do. But what always surprises me is how unused to looking at satellite data people are, because, I'm used to, like, I always have satellite view on my maps. Like if somebody shows me like,
Same.
Oh, can you show me where whatever, and it's not in satellite view, I'm like, what am I looking at?
What are these shapes?
Yeah, exactly. I'm just like so used to seeing the world from, or, where we are from above. But often like at conferences or presentations, I love to show like, a Sentinel-2 optical satellite image of the place we're at like the day before or whatever the most recent observation was.
Just to freak everyone out?
Yeah. Well, to be like, do you know where this is?
Oh, okay, yeah.
And it's not very common for people to know, what the place that they are at looks like, let alone, many other places on Earth. But we have these incredible resources freely available for fun and research.
And okay, so the research part of it, these incredible resources you're using, is specifically agriculture, part of your work, right?
Yeah.
One of your projects is Fields of the World, which is trying to build a global data set of where fields start and end and what's in them.
Yeah.
So I was could you tell me a little bit about that one?
Yeah. A big area that we look at with satellite data and machine learning to really inform the kinds of methods that we're developing for the whole field, but then also developing specific solutions for applications are in agriculture, because there's so much involved in agriculture, right? Like we all eat, for one.
Yes,
we need food. It is grown in fields still, for the most part. And it's also, a huge driver of the economy. It's a huge driver of people's livelihoods. It's a huge driver of climate change and our changes to our environment and landscapes. It's also hugely affected by those changes. All of this boils down to having a fundamental piece of information about where are the fields, so if we want to do things like estimating what a field is going to produce at the end of the season, or trying to detect where there might be pests and disease early, if we want to look at policies like the EU deforestation regulation, which aims to only source food of a certain set of commodities from fields that did not experience any deforestation, how much nitrogen I should apply, or how much fertilizer, how much I should water. All these questions boil down to where's the field? What is the unit, right? Because without an actual field boundary to use in these analyses, we're limited to pixels, and the pixels are not really, in sync with the unit that we want to analyze there. Sure.
So, okay. Probably a dumb question. Why don't we know where the fields are?
Yeah, it seems like, farmers know where their fields are, obviously.
Right.
But for one, there's just a huge variability in terms of data collection about agricultural fields and farming practices and farming activity in different countries around the world. So, for example, in a lot of European countries, do require farmers to report where their fields are and certain characteristics about them, about, maybe what they planted or what practices they might use, because there are different subsidies or benefits that might come from the government. So there's a systematic required reporting there. And so we do know where all of the fields in France are, for example, because
Good job, France.
Farmers have been required to report them.
Yeah.
And that's true of a few other European countries as well. But in many other countries, that information is not collected by the government, which is very expensive to do. And maybe if it is occasionally collected, it's probably for a survey, a select random set, maybe of fields. It's not all of the fields. And in many countries, there's just not data collected about this at all.
It's one of those things that it's insurmountable when you think about the scale of the problem. Well, maybe not insurmountable because you're working on it, but it's a big problem when you think about the scale of it. But it also, without ever thinking about it, it's we would just know that.
Right. Yeah. Well, and depending on who you talk to, people are interested in different things for agriculture, right? For a lot of farmers, they're like, why, I don't need you to tell me where my field is or what type of crop I planted, right?
I imagine there is some tension between it's none of your business.
For sure. And that's something that we've done. We have in all of our projects with agriculture, we have really close relationships with farmers where we're working and trying to co-develop these solutions to make sure that they're not just, in part of this extractive loop where we're recording information about them, taking data about them that, they're not necessarily part of the process in, and trying to make sure that we're designing solutions that give value back to them, not just to higher level decision makers, who need to, for example, estimate agricultural production statistics.
So tell me about some of the solutions you're designing then, because to not get people stuck in this extractive loop, what kind of information are you providing to farmers?
Yeah. So one example is a project that we have under the NASA ACRES program, which is NASA's food security and agriculture program. under applied sciences that's focused on the United States in particular. This came after NASA Harvest, which still is running now, but is a similar program, but focused globally, including the U.S. But ACRES is specifically looking at the United States. And we have a project under that in Maui County in Hawaii, where we're working to support increasing food production in a way that promotes indigenous farmers and aligning with the community goals and values of increasing food production while taking care of the Aina, or the land. So there we have really close relationships with a lot of farmers because there's a huge amount of skepticism about surveillance and how data might be used to target people or make decisions that are not really happening with them. So some of the solutions that we're working on in Maui County that we've co-developed with farmers and local community organizations is our Maui Nui Crop Monitor. So we produce a newsletter that goes out in email that's looking at the ecological conditions, basically weather patterns and climate patterns, things that are related to agriculture production, and giving information to them about, like what is the current state of rainfall in different regions, so soil moisture, drought.
Might be good to plant sweet potato coming up or something.
Yeah, we include, I'm not a farmer. Right. And many people there are new farmers. And so we've heard from local farmers there that are new farmers in particular, that they really liked having this Kalana Mahina planting calendar that is based on Native Hawaiian planting cycles that are based on the moon phases.
Oh, cool.
And so they would see this information in there about, like, according to this calendar, now's the time to plant taro, or now's the time to do that. And so we align that with NASA data about precipitation and other, temperature, other information to kind of give insights on what's actually happening according to the data, to help calibrate with people's local observations about what's happening on their fields.
So to connect the 3 points we've talked about, so all that data from the satellites is being fed through a machine learning algorithm that then turns it into actionable information, like this calendar you're talking about for farmers.
So the calendar was actually developed by Native Hawaiian communities. That's something where we're bringing in additional expert knowledge. Yeah. In our newsletter, yes, we have this data coming down, and we use that to develop maps of like where crops are growing and intersect that with other information about what crop conditions, trying to predict what crop conditions might be based on a combination of that weather data and our maps to give information to farmers.
Have you had the opportunity to go to Maui County and like see these farms?
Yeah, cool. We go very frequently. At least once a year.
Oh, tough job.
And every time we make sure that we're actually visiting the farms, and, not just in Maui, but in a lot of our projects globally, there's just no way you could understand the scope of the problem and develop effective solutions without actually seeing it for yourself.
Right.
Some of these challenges that we're trying to solve globally are things like, how do we create these maps of where maize or corn is being grown all over the world? And in many places, maize is intercropped with other crops. So there will be, some maize here, some soy there. And so without seeing these kinds of patterns, you're not going to understand like what is captured or what is maybe not captured in the ground truth data. If somebody recorded maize in a field, we wonder, was it just maize? Yeah. What else? Like, let's look at the signature, so these are all, you just can't treat these data sets as toy data sets like you might do in a, class on the basics of machine learning.
Sure. I have to imagine that like the algorithm's not going to be able to figure out what's maize versus, I don't know, again, not a farmer, throwing things out there, maize versus like soybeans, or wheat would be easy because it's a different color, but just looking at an image of it, because there's a lot of factors there at play, right? There's different types of corn, there's different types of soybeans. Like it can't just like do a color and say, oh, it's this one, right?
Yeah. Well, and especially, you might think like, oh, I can identify these crops if I'm in the field looking at them. Sure. But remember, the satellites are, many, many, many kilometers up looking at them. And so we don't see like these, close like shapes of maize leaves and things like that. Maybe we can see some texture of how, rows are planted depending on the satellite. But most of the time, we're seeing a color, right? And what's incredible about satellites, though, and gives us the ability to extract that information of like, this is maize versus that's soy versus that's wheat, is that we don't just have the like red, green, blue color that we're used to seeing. Yeah. We have the color in other wavelengths of the electromagnetic spectrum. Okay. And we have that pattern through time, right? So we have the pattern of many, many different wavelengths of color, but also crops are specific in how they grow over time. One crop might be planted later than another or reach a certain color at a different time. So this combination of spatial, spectral, and temporal information is characteristic of what a crop is.
If you enjoy conversations that spark curiosity and make science easy to explore, check out Ask a Biologist, another podcast from Arizona State University. Hosted by Charles Koselik, aka Dr. Biology, each episode invites listeners into the wonders of the natural world, from animal behavior and the human body to the big questions that scientists are asking about life on Earth, in a way that is engaging, accessible, and fun for curious minds of all ages. Discover new episodes and explore hundreds of science stories, activities, and resources at askabiologist.asu.edu and wherever you get your podcasts. So earlier you mentioned NASA Harvest, and you mentioned that's a global effort. And I think you're the machine learning lead on the project. Are you focused on one region, or are you looking at things all over the world? And then how do you then teach algorithms to interpret data sets from different places, because different places plant different crops or the same crops differently?
Right. Yeah. So we are focused globally. We have several projects that have a local focus spread globally. So for example, we have a project with the famine early warning system that we've been working on for many years, where we're trying to assess the impact of conflict and other shock events on agricultural production in a region, for them to inform their household economy analysis, understanding where people might have shortfalls of economic value when they're selling crops, or shortfalls of nutrition if they're not able to access food. And in that project, we focus largely on Africa, East Africa in particular. We've done studies in Tigray, in Sudan, now with the active war there. Within Harvest, we have many different projects that together probably do cover the globe, but we're also working on developing systems and solutions that could work anywhere, because we don't know. There's always a request for some analysis or a need in different places. So we can't just design solutions that only work in one place.
For sure. So one challenge in your research is unlabeled data, right? And that can be a challenge to train models on unlabeled data. But recently, and I say recently for normal people, not researchers, recently there's been examples of progress with models that use unlabeled data to do self-supervising training, namely LLMs, large language models like ChatGPT or Claude or what have you. Basically create a large Earth model with unlabeled data and self-sustaining training. Is that right?
Yeah. So basically, for so long, our ability to use machine learning for satellite data, analyzing satellite data for a given application, let's say, a insurance company in Mexico wants to look at expected crop yields to see where they can give assistance to certain farmers. They would, in order to create a map like this, like a crop type map, identify where is maize being grown, they would have to start from scratch, like creating their own model, collecting labeled data. This is maize, this is not maize.
Yeah.
And the same is true for every single person who needs a model to do one specific task. It's always starting from scratch because it relies on having examples, labeled data of what you want to find in order to get started. The difference with the opportunity we have now with self-supervised learning, which is learning from unlabeled data, is that now we can actually make use of these petabytes and petabytes of satellite data that are just sitting in these archives, where before it's like, well, maybe we're not using that because it's not labeled or it's not for this particular task. So we don't necessarily know what's there yet. But now with self-supervised learning, pre-training models, or foundation models, whichever term you want to use to talk about them, is we can train models on all this unlabeled data to learn what the patterns there are, basically study the archives, be prepared to solve any new task that might come along. And so now these models should be, much farther along when we need to get started for a new application. So the idea is that we can use that model now as a starting point, and I need a lot fewer examples to do a specific task. So I don't have such a huge bottleneck for labeled data because I've already learned a lot of what's there. I just need a little bit more to specialize to a certain task.
That opens up a lot of possibilities for what you could accomplish with these. It
does. It would open up a lot of possibilities. And satellite data is like the killer app for self-supervised learning because it's like, oh, unlabeled data, like, we've got that. We've got tons of it. We have so much of it. So we're like, okay, like there's no way we would ever have been able to touch every single one of these pixels with a model before. And so there's huge opportunity there. And we're starting to see progress on actually hitting those benefits of less labeled data required, faster adaptation for users' new tasks, and getting these models into the hands of users. But we still have a long way to go. We're still not seeing this, explosion of improvement, this like incredible progress that we've seen in language models yet.
How far do you think we are from a mature large Earth model?
I don't know. I think it depends on us as a research community. I think, if we all can really put our efforts into trying to come up with solutions that are designed for the patterns of the data as it is, rather than trying to, lift and shift methods from language. There's certainly a lot to learn, and there are a lot of similarities in terms of patterns that you might see in language or patterns that you might see in regular consumer images compared to what we see in satellite data. But there's also huge differences. And I think what we're seeing when we adopt those methods directly from images, what we call natural images, which is like our, camera phone, internet style images, and from language models, is that we're really hitting a ceiling. We're making all these little improvements on these model architectures and, maybe beating the metrics by a little bit, but it's still not that much better than if you had used a language model or a vision model pre-trained on not satellite data at all off the shelf, or even doing that, task specific, fully supervised model. So, if we're going to get these huge transformative gains, we really need to come up with things that are totally different. And I don't think that's far off technologically. I think it's a matter of community focus.
Okay, so OpenAI has ChatGPT, Anthropic has Claude. There's other ones I'm forgetting, I'm sure. But if you had to coin a name for a large Earth model, what would it be? Go.
Oh, we have so many names already.
Oh, yeah?
Yeah, I'll tell you. I mean, our favorite, I still love, we've developed multiple models, foundation models, self-supervised models for remote sensing data. The first one we did is still my favorite. It's called Presto, which is pre-trained remote sensing transformer.
Presto's pretty good. I like Presto.
Yeah, we've never thought of a name that I love as much as Presto because it captures so well what that model does and is good at, which is being really fast and efficient. But yeah, we then had Galileo, which is like a tortured backronym.
Okay.
I can't even tell you.
Presto is not a tortured backronym. Like that one works. Like yeah, that one works well.
Yeah, but I still love LEM because it's like the lunar exploration module of, you know, Apollo times. So I love the tie of, you know, looking at our planet, but, you know, building on these decades of technological progress that's been made in space exploration.
For sure. A lot of your work is federally funded. So for people listening, what are some of the biggest kind of taxpayer benefits that you see from the research that you've been doing? Yeah,
I mean, for a lot of these things that seem maybe kind of archaic about like how much food is being produced, that feeds into things like what commodity prices are in the markets. And that feeds into things like how much our groceries cost, right? The more we have accurate information in this agricultural supply chain, the more we're getting kind of like fair prices for our food and access to our food when we need it. The solutions that we're developing are used by urban planners or people in governments and communities to look at like what is the land cover, like where are buildings maybe too close to things that they shouldn't be? What are the wildfire risks of the way things are right now?
Important.
Yeah. We do a lot of work on rapid response when there's a disaster, who's being impacted. A lot of the rapid insights that we're providing are for unlocking benefits to individuals, whether they're farmers or just residents, you know, to benefit from programs that can aid in a crisis. So one example in Hawaii and Maui after the devastating wildfires in Lahaina and other places in the county a few years ago, we quickly worked with Maui United Way to develop an app that included our wildfire extent maps and building damage assessments from our collaborators at Microsoft. And then Maui United Way could then use that to basically verify claims from people who were seeking financial assistance.
And get them to aid faster.
And so, you know, within days, they were releasing $1,000 to every adult, not just every household, but every adult affected by the fires, which was enabled directly by these data sets we'd been developing. And of course, we didn't develop those solutions in a day.
Sure.
These rapid solutions, like you can't predict what you're going to need when you're going to need it. But by having the investment in developing these kinds of solutions that we know will be useful in these kinds of scenarios, we have them ready when we need them. And we've seen that in crisis after crisis, whether it's food, fire, floods, etc.
That's so cool. So earlier you talked about how you only have like Google Maps on satellite view, which I have to imagine looking at satellite data all the time must change your perspective on things. Can you expand on that a little bit, if that is true at all?
It does. And most of the time it's like, you know, I'll be I don't know, I'm thinking of scenarios where I'm like looking at something and I'm like, man, this must look so crazy from satellites. Like I'm always thinking like, I remember being at the top of a mountain we had hiked on in Germany, and I saw just like so many different types of trees. And I was like, ooh, like from above, like there's so many different tree species. Like, I wonder what this looks like. And at what point does that start to blend, you know, because there's just so many scales of what we can detect and why and when. So yeah, it definitely makes me think, you know, what does this look like? Or I wonder, I'm always finding myself being like, well, can we see this if I'm somewhere and I'm like, man, it looks so dry here. Like, is it usually this dry? You know, I know how to access that data and find out. And what I want to do is make that kind of information easier and faster for everybody to access.
Have you ever played GeoGuessr?
Yeah, I have played GeoGuessr. I think I'm good at GeoGuessr because I'm good at noticing little clues, not because I know what things look like, but we're like, what's that language? You know, like I've been to so many places through this work that I'm like, those stop signs look like the ones that I saw in this place, you know?
All right.
But yeah, my lab and some of our like fun, you know, lab retreats or activities, we have played GeoGuessr together.
Yeah. Okay. Yeah. No, I haven't played for like a year, and I was never like ranked or anything, but like I was pretty good at GeoGuessr, and I attribute a lot of it to just like being a weird nerd who looks at like satellite data because like I think it looks cool and it's interesting to me.
Yeah.
You know?
Yeah. I mean, I encourage everybody listening, go on Google Earth and look up your location and pull up the historical imagery viewer and just see like how things have changed over time. Even in this area around ASU, I love to look at because it was so different before.
Yes. Become a weird nerd. Get into satellite data. I'm applying that label to myself, not necessarily you, but if you want to be a weird nerd, you're welcome to.
I think I can identify with being a weird nerd.
Awesome. Great. So Hannah, this was super fun. I loved like being a weird nerd about satellite data with you. If anyone wants to learn more about some of the topics we talked about today, do you have any like suggested resources or reading or watching or what have you?
Yeah, there's a cool podcast called Satellite Image Deep Learning, which is basically what we've been talking about by Robin Cole. I think that's a cool podcast where you can learn about like a lot of these, you know, specific models that we might be talking about.
Okay.
Well, I'll be doing an episode with him on Fields of the World.
Awesome.
I also really enjoy reading a Substack by Christopher Wren called Applied Geospatial. It's kind of a more like skeptical look at the field and looking at, you know, how well are some of these things that in the news might be super hyped, just looking at like, can I use this to find where crops are for, you know, very applied things. Yeah, just in general, I don't read a lot of books that are about my like specific area because I know it. Yeah. But I'm really enjoying reading Empire of AI by Karen Howe right now.
Those are great recommendations. And, you know, go get on Google Earth, play around, have fun with it.
Yes. Know? Yeah. Our Google Earth Engine also is a very fun tool with a lot of tutorials. Okay, great. Hannah, thank you again for joining me. Thank you. Thank you for tuning in. That's it for season 2. We're going to take some time off to develop our next season, but keep your eyes on this feed. There might be some bonus material popping up in our downtime. Lab Coat Optional is a production of the Strategic Marketing and Communications team at Knowledge Enterprise at Arizona State University. Knowledge Enterprise is led by Executive Vice President Sally C. Morton. If you don't mind, leave us a funny comment or a 5-star review. You can even roast me. I don't mind. If you make me laugh, I'll read it out on the show. And if you found us on YouTube, do the 3 things: like, comment, and subscribe. As always, lab coats are optional for this show, but we want all our researchers to stay safe in the lab, so wear your PPE. See you in a few months. In the meantime, stay curious.